So after the dienes and the stability of the dienes, we talked about the addition and also the overlap of the atomic orbital, like a side-by-side atomic orbital that gives you molecular orbital. So low energy occupied molecular orbital or high energy unoccupied molecular orbital. These are the orbitals that they are as a result, they are forming as a result of destructive overlap. You see the positive and negative, and then you have a positive, negative, positive, negative. If they are both positive, this is constructive. You have both positive, constructive. And this pattern, it gives you pi 1 with the lowest energy. You get the pi 4 with the very high energy, because everything, every consecutive overlap is a destructive one. And you have the other ones that are in between. Some of them are constructive and others are destructive. The type of reactions that I said I'm going to cover today that we didn't talk about is Diels-Alder reaction. For the Diels-Alder reaction, which starts here. The other name for Diels-Alder reaction is called cyclization. That means a cyclic system is forming. There is another name for it, and it's called a 4+2 cyclization reaction. But when you talk about Diels-Alder reaction, the both 4+2 or cyclization is kind of understood in there, in the term. What's happening in a Diels-Alder reaction? You do have a diene, and the diene that we have here is like a 1, 2, 3, 4. So this is a 1,3 butadiene. So we have a diene. These are the components or the reactants that are reacting in Diels-Alder reaction. One is a diene, and the other one is called a dienophile. What makes a dienophile a good dienophile? What's the primary condition? Primary condition for dienophile is that it must be a carbon-carbon, either double bond or triple bond. So if you have a carbon-carbon double bond simply like a C-C bond, this is a dienophile. If you have a triple bond, that is a dienophile. So if you have a double bond with electron withdrawing group, that is a good dienophile. If you have a double bond with 2 withdrawing group, then it's going to be very good dienophile. So very good dienophile. So if you have carbon-carbon double bond that is attached to electron withdrawing group, is going to make that dienophile even better dienophile. Heat is required for the reaction. So we talked about the general format of the reaction in Diels-Alder reaction. You start with a diene, and the diene must be a conjugated diene, and it must be if it's conjugated, that means that 2 pi bonds are separated only by 1 single bond. So we have like a 1,3 diene here, or 1,3 butadiene. This is the simplest diene that can go through the Diels-Alder reaction. Now, can the structure for diene be only like the way that we have in this example? No, but as long as you have that structure of 1,3 diene, so it could be part of a cyclic system. It could be a molecule that it has the diene, but it also is attached to another group. Let's say you have a CH3 here, or you have a ethyl group here. So any group can be on the diene as well as the dienophile. What makes the diene a better diene? One is orientation. if you have a cis diene versus trans diene, remember said that if you have the two double bonds in opposite side, that is a trans diene. Trans diene is not perfect or is not ideal for Diels-Alder reaction. And why is not ideal? Because if you look at this, you have the final product is a cyclic system. So if it's trans, there is a rotation required here. That's going to slow down the reaction. But if it's already cis, it's kind of ready to go and form the cyclic system. So a cis diene is preferred over trans diene. If it's a trans diene that is restricted in a if it's restricted in a cyclic system that you cannot turn it around, twist it to change to cis, then that diene is not even good at all. It cannot go through Diels-Alder reaction, because if you have an open chain trans, this can go to cis configuration. But if you have one that is restricted, let's say you have one diene that is part of a cyclic system, and then you have this one. It's, even though it's conjugated, okay, it is trans, but is restricted in this molecule in a part of the cyclic system, is not going to be, you're not going to be able to twist it with the room temperature or the reasonable amount of the heat that you provide to change it, to bring it to the opposite side in order to make it cis. So this is not going to flip over, this part of the molecule is not going to flip over to give you cis. So it's not a good diene. A perfect diene would be a cis diene. I mean, that's a good diene. A perfect diene would be a cis diene with electron donor grouping attached to it, like alkyl group attached to it. So if you have alkyl group attached to it, it's even better. So it must be conjugated, okay? It must be conjugated, and it must be, it must be conjugated, and it must be cis. And if you have electron donors group attached to it, it makes it even better diene. What about the dienophile? When it comes to dienophile, one more time, it can be double bond, carbon-carbon double bond. It can be a carbon-carbon triple bond. But if you have an electron withdrawing group attached to it, it's going to make the dienophile even better dienophile. So it makes it better dienophile. If you have another electron withdrawing group attached to the other carbon, it's going to be the excellent dienophile. So based on the experimental data, it's showing that if you have electron withdrawing group, it's going to make this reaction happen much faster. So those are some of the conditions. So what is happening in general in a Diels-Alder reaction is that you get your, okay, I'm going to label this A and B, the 2 carbon from dienophile with 4 carbon from diene is going to form a cyclohexene. Okay, how this is going to take place, if you look at these the pi bonds are going to break. So these are the baby steps, but it's going to help you to memorize it better. So 3 pi bonds is going to break. Okay, 3 pi bond will break. That's like 6 electron. 2 sigma bond is going to form. 1 sigma bond would be between carbon 1 and carbon A, carbon 1 from diene, and carbon A from dienophile. Another sigma bond is coming from carbon 4 from the diene and carbon B from dienophile. So let's say this electron, when you break this pi bond and 1 electron goes up, 1 electron goes down, these 2 electrons is going to be consumed here. When the pi bond between carbon 1 and 2 breaks, 1 electron goes to carbon 1, which needed for this bond to form. One electron goes to carbon 2, and so you have an electron here on carbon number 2. And same thing here, you have one electron that is going to form bond with carbon B, and one electron goes to carbon 3. So the electron that goes between carbon 2 and 3 later is going to form a new pi bond. So we see that 2 sigma bond, these are the sigma bonds, 2 sigma bond, these are the new bonds, 2 sigma bonds form, and 1 pi bond. You break 3 pi bonds. So 3 pi bonds, 3 pi breaks, 2 sigma forms, and 1 pi bond forms. The 1 pi that is forming is between carbon 2 and 3, C2 and C3. This is the general structure. Now, anything and everything that is attached to dienophile is going to stay the same way that it was attached before. So if I bring these labels over to the product side, I have 1, 2, 3, 4, carbon A, carbon B. What do we have attached to carbon B on the reactant side in the dienophile is the nitrile group is going to stay. The new bonds that are forming, 2 sigma bonds, these are the 2 sigma bonds that are forming, and this is the pi bond that is forming. Okay, so 3 bonds break, 3 bonds form. Would you think this reaction is exothermic or endothermic? At the beginning, it does require heat to break, but since 2 sigma bond is forming and 1 pi bond, here you are breaking 3 pi bonds, I think this reaction is going to be exothermic reaction because sigma bond is stronger and is going to release more heat. So anyway, the final product is going to contain additional cyclic system, at least one cyclic system. If your reactants contain a cyclic system, if they do have one, if one of them is a cyclic system, then the product is going to be a bicyclo. So what happened here? This is your diene, and I'm going to label it 1, 2, 3, and 4. The next one, your carbon-carbon double bond here is dienophile, and that's your carbon A and carbon B. So for the first couple experiment reaction, for the students, I usually label all these and carry it over to, for them to see what is the orientation or what's happening. Okay, so you see that this part of the molecule, 4 carbon from diene and 2 from dienophile, formed a new cyclohexene. So formation of a cyclohexene is another name for Diels-Alder reaction or cyclization or 4+2. So what are these groups here? This group here is like an electron withdrawing group because carbon here is positive. So it's electron withdrawing group attached to this dienophile. It's going to make it a stronger dienophile or better dienophile. And same thing here is the electron withdrawing group attached to dienophile. Whatever is attached and the way that they are attached is going to stay and copy itself on the product side. So we have a cyclic portion of the dienophile that is going to be copied over. The only change is that these 3 pi bonds are breaking, okay? And 2 sigma bond is forming and 1 pi bond is forming. Any questions so far?
Professor, I think, can you just repeat what makes a good dienophile?
What makes it good dienophile is the presence of electron withdrawing group attached to the dienophile. So if you have a CC double bond, that is a dienophile. But if you have a electron, W represents electron withdrawing group. It's not a group on its own. So it can be like a COOH. It can be ester. It could be like this W could be this. W could be like an ester, COOCH3. That's electron withdrawing group. These are electron withdrawing groups. So if you have electron withdrawing groups attached to the dienophile, it's going to make the dienophile a better dienophile. Any questions? No. Okay. On the next example, we have the first part, which is the diene stays the same. I'm just going to use the same colors for numbering 1, 2, 3, and 4. Your carbon A and your carbon B are here, carbon A and carbon B. Now, only one pi bond of the dienophile is going to break. Your dienophile could be double bond or it could be triple bond. If you listen to the first part of this recording later, you see, I said that it could be a double bond or it could be a triple bond. Both of them are dienophile. And only one pi bond breaks. So one pi bond breaks. On the product side, you are going to end up with another pi bond. So this would have been just a cyclohexene with no pi bond if you had a CC double bond here. Because it's a CC triple bond, one of the pi bond would carry over. The group that is attached to dienophile here, the ester functional group, is the electron withdrawing group, and the way that is attached is going to stay and it would carry over. Anything attached to dienophile or attached to diene is going to stay. So if you already have one cyclic system, it would be bicyclo. If you have extra pi bond on the dienophile, it's going to also stay. Let me know if you have any questions about these two. Now, we said for diene, I'm going to number it again, 1, 2, 3, and 4. Dienophile A and B. Okay. So diene and dienophile is going to be just the basic part of it. It will stay the same. The others, whatever we have attached to dienophile or attached to diene, is going to carry over as well. So this is electron withdrawing group, so it's going to make this dienophile better dienophile. This is electron donor group. Electron donor group is going to make the diene a better diene. So it activates the diene. If you have electron donor group on the diene, it would activate the diene. And dienophile, if you have electron withdrawing group, it will activate the dienophile. A new bond forming, old bonds are broken. Here you have 3 pi bonds that will break, and then you have the 2 sigma bonds that is forming and 1 pi bond that is forming. So the ones that I'm marking red color here, those are the new bonds on the product side. And then you had 2 methyl group, one attached to carbon 2, one attached to carbon 3, it carried over. You had a nitro group that it did carry over to the product side as well. If you have one of your diene or dienophile already in a cyclic form, your product is going to be a bicyclo. How would you draw this bicyclo? Very similar to the cyclic system that you have. You don't have to even make it like out of the plane here. So you could number it the same way. 1, 2, 3, 4. Why do I call always these 1, 2, 3, 4? Because these are the ones that I'm interested in Diels-Alder reaction. This is for carbon A, and that is a carbon B. So if you just draw this structure like this, is going to work. Okay. You break this pi bond, break that pi bond, and break one of these pi bonds. So basically, you get the cyclohexene. But since dienophile had a triple bond, one of the pi bond did carry over. Anything attached to the dienophile stays. Anything attached to dienophile stays. Anything that is attached to diene is going to stay as well. Okay, anything that is attached to diene is going to stay. There is a carbon between carbon 1 and 4, and this was your carbon 1, that's the carbon 4, and you have the carbon that is forming this triangle, which is basically a bicyclic system. Just pay attention if you have a cyclic system to begin with. On the product side, you would get a bicycler. What else you want to pay attention is that if your product, when the product forms, there would be at least one pi bond. So if you have this cyclic system with no pi bond, that's not a product of Diels-Alder reaction. The product of Diels-Alder reaction has at least one 6-membered ring and at least one pi bond. I'm telling you because in multiple choice questions, you would see that the product looks like Diels-Alder reaction, but there's no pi bond on the product side. Then there is no, that's not the product of Diels-Alder reaction. Or if you have no 6-member ring, here's the 6-member ring. You have 1, 2, 3, 4, 5, and 6. So you do have the 6-member ring, even though it doesn't show like a standard 6-member ring, but you still have the 6-member ring. You have an additional ring here, which makes it bicyclic, but that's okay, but at least one. You have at least one pi bond. So that's also okay. In this case, diene is in cyclic system, and the diene is in cis form, which is good. 1, 2, 3, 4, and the same thing is going to happen. Okay, a pi bond will form. You have at least one pi bond. Your diene was a cyclic system, so you get a bicycler because this reaction would give additional cyclic or cyclohexene would be one of the major part of this molecule is formation of a cyclohexene. Whatever is in addition, it will stay. So anything attached to the diene will stay attached to the diene. It doesn't change. Whatever you had attached to the dienophile, that is going to stay and is attached to the same carbon that you had in the dienophile, because this is 1, 2, 3, and 4, and this is your carbon A and carbon B. Questions? We get a lot of these questions on the quiz, so I just want to make sure that we do go over of these reactions. Okay. So breaking the pi bond and formation of the single bond, that's what we have. The red colors are showing the new bonds that are forming. The conditions, I talked briefly about the difference between the cis and trans. The cis and trans, if you look at the size of this double arrow, it says that this can go back and forth. That's okay, it can go back and forth, but can this go back and forth? This cannot go back and forth because there is no carbon-carbon single bond here that is outside of the ring, and as a result is not going to attach to is not going to rotate, because in order for a diene to go through the Diels-Alder reaction, first it has to go to a cis position first. Okay, it has to go to cis position first. Now, in order to go to cis position, it cannot be restricted. You see, this single bond is part of a cyclic system, and it cannot be rotated. And since it cannot be rotated, no Diels-Alder for this molecule. This one is restricted to a cyclic system, is already like in place as a cyclic form, that is not going to go back. There is no way for this to go back to trans, so it's ready to react. And since it's ready to react, it can form the bond with the diene, which is the A and B carbon here. And that's the 1, 2, 3, 4. So it can go through Diels-Alder the fastest because it's a restricted cis. Okay, this diene is good because you have the 2 electron withdrawing group on it. So for the butadienes, electron withdrawing group is going to help. At the same time, you don't want your electron withdrawing group to be like it would cause like a steric hindrance. So if it's hindered like this, it's going to happen. The reaction will happen. This will go through this other reaction, but it's going to be harder. So it would just slow down. Okay. So transdienes cannot undergo. So we have a transdiene here that is restricted transdiene. It will not go through Diels-Alder reaction. And some of the questions actually involve which one is best or which one is fastest.
Professor, I had a question.
Yes.
Well, so you would never really see hexadiene become a diene and form another, or you would never see your starting diene be a hexadiene because the goal is,
Hexadiene.
yeah, would that ever happen, or because the double bonds are already in a ring, it wouldn't extend itself to making a new ring?
Okay. If you were going to make the hexadiene to be a part of the Diels-Alder reaction, then your hexadiene it should be in this shape. Okay. Yes, this hexadiene can. This can go. This can go, and it can actually make a new ring. It can make a new ring. As long as it's cis and is a. But if you have a hexadiene like this, that one of the pi bonds are outside of the ring and the other one inside the ring, and there is no single bond rotation, possibility of single bond rotation, then this is not going to go through diene. So this cannot go through Diels-Alder, no. But let's say if you have a cyclic system that looks like this, if you just look at it, pay attention, you see you have this, and then you have this trans. There is a single bond here. This is a carbon-carbon single bond. The rotation around this carbon-carbon single bond, it's possible. So this carbon can be rotated to the other way. And when it does rotate, okay, when it does rotate, you will get this. So this side of the molecule is going to give you 1, 2, 3, and 4. You see the difference? In this case is like restricted to the ring. You cannot, there's no rotation. But in this example right here, in example A, there is rotation around this carbon-carbon bond shown with a purple color. There's a rotation, possibility of rotation there. And then when it does rotate, it changes to cis. But this rotation is not allowed because you cannot bend this, you cannot bend the cyclic system. But if your diene is in the cyclic system, cyclohexane even, cyclohexadiene, it's possible as long as it's conjugated and is in the cis position. It can go.
Okay, that makes sense. Thank you.
You're welcome. Okay, so if you look at some of the geometrical structure of these dienes and the dienophile, see that you can get, if you have a cis di-substituted diene. So this is a cis dienophile, sorry. If your dienophile is going to be, so it's basically stereochemistry. This is like a little bit more in depth. So if they are on the same site in the diene or dienophile, the product is going to be in the cis form. Okay, in the new compound that is forming, they will be in the cis position or on the same side. So see that you have this a cis dienophile. This side of the molecule is going to be cis. So you have a cis compound. So if it's a cis, you would get cis. If your dienophile is trans, see that these groups are on the opposite side of carbon-carbon double bond. If your dienophile is trans, then the groups, these two groups on the cyclohexane, they would show in opposite sides. So you have a solid triangle and you have a dashed triangle. So they would be trans. So if you have a trans dienophile, it would yield to trans product. And these are other examples that if you have the methyl groups, the same position, like in the vertical position, like let's say if you consider this as like a equatorial or the axial, right? So if you have them in the axial equatorial, both of them like in axial position, that would make more sense because it's going to cyclohexane. So for the diene, if the groups are on the axial position, then both of them is going to give you cis product. But if one is axial, one is equatorial, looking like, your product is going to be trans. So on the product side, the groups that are attached to dienophile, they would be in the trans position, one going away, one coming toward you. So for the dienophile is easy. If it's cis would be cis, if it's trans would be trans. And then for diene, when you are drawing, if they are in the carbon 1 and 4, if they are in carbon 1 and 4, if it's carbon 2 and 3, the way that they are is going to copy. But if it's in carbon 1 and 4, if they are like equatorial axial, then you would get trans, like this example. But if both of them are in the same position, it would show you as a cis product. This is probably the most challenging part of it. So it's not like, that's why I said the addition is kind of a endo addition. So it's trying to get to the, it's going to be more stable. If you have a bulky group, the more stable configuration is if you have the group that is a bulky is going to be in the equatorial position rather than the axial position. So it's going down, away from the ring. So the electron withdrawing group is going to be in the endo position. So exo it's like coming toward you. Is showing with the wages, and then endo is going away from the view, and electron withdrawing group would be in the endo position. And if you get a multiple choice questions that which one is like more stable, look for a structure that would give you electron withdrawing group in the endo position. Okay, this is just extra examples, very similar to what you had before, with just one specification that this bicycle is going to form, cyclohexene is going to form. So you have your cyclohexene, and then you have your electron withdrawing group from dienophile that is going to go to endo position. It's going to go down to endo position. Okay. And these two groups, like because it's in the cyclic form, the whole cyclic system is going to go in the away from the ring or in endo position, just to avoid steric hindrance. And then you have some solved problems, and that has to do with the position of the branches that you have, if it's a 1-3 or if it's going to be 1-4 with their relationship. If it's a 1-3 or 1-4, you would get a specific configuration for it. Let me go back. So there's just a couple slides of that I don't want you to be too worried about it. Just know that if you have the groups, electron withdrawing group from the dienophile, if they're in the cis position, it would be on the cis position on the product side. And then the electron withdrawing group, it is going to go to the endo position. Those are the ones that I want you to be worried about. And we talked about the overlap for the high energy, low energy. So you have a bonding and anti-bonding. For the bonding overlap or bonding pi-bi, you have constructive, and for anti-bonding, you have a destructive overlap. And when you have more than one pi bond forming, then you get the combination, how many constructive and how many destructive. So if you have the highest occupied molecular orbital, lowest unoccupied molecular orbital. So when we're talking about HOMO, that's the highest occupied molecular orbital, and then lowest unoccupied molecular orbital. When we talk about the UV spectroscopy later on, basically excitation is going to happen from the highest occupied molecular orbital. One electron would go from this level to the lowest unoccupied molecular orbital. And then when it comes back, it would give energy. That the HOMO and LUMO term is also used in UV spectroscopy as well. So when the energy is absorbed to go up, the same amount of energy would be released when it's coming back to more stable situation. Electrons, if they are in the bonding orbital, they are going to be more stable. If they are in anti-bonding, they are less stable. That means they have more energy. In order to take electron from bonding orbital to anti-bonding orbital, you have to give energy to it. The amount of the energy that is given, it's equal to the amount of the energy that is coming. When it's coming back, it would be released. It's called excitation, relaxation. So when excitation takes place, it's hard to measure that amount of energy. But when relaxation takes place, this energy, when it falls, the electron falls down to lower energy level, energy would be released. When the energy is released, it's going to show a band like a green color, red color, orange color with a specific wavelength. And as soon as you have that wavelength, you can then calculate the frequency. If you have the frequency, then you can calculate the energy of that. You can calculate how much energy has been released. and you can calculate the difference between the occupied and unoccupied, how much energy difference is between the two, which in UV spectroscopy, this amount of energy is being calculated with specific information for the UV spectroscopy. The larger the molecule is, the distance or the energy difference between the HOMO and LUMO is going to be smaller. So larger the molecule, you get longer wavelength, which is lower energy and is like more into the visible light region. The more pi bond you have, then that distance is going to be lowered. So you get lower distance, lower energy difference, and less energy needed to excite electron. If you have one molecule that is, it contains 2 pi bonds, same number of carbon, and one is conjugated, one is isolated, the one that is conjugated, the lambda max is going to be greater for A compared to B. So greater lambda max, that means less energy. When there is a conjugation, the difference between the energy difference between the occupied and unoccupied is going to be just shrink, and it gets lower. So if they are the conjugated dienes, they have MOs that are closer in energy. As a result, it takes less energy, and this amount of energy can be calculated in UV spectroscopy. And using the data from UV spectroscopy, you can actually say if your molecule is conjugated or if it's isolated, if it's more stable or less stable, how many pi bond does it have, or how many carbon does it have. Okay. We talked about this already, and you might get a question on the exam or the quiz. Pay attention to these phases, or if the overlap, is it constructive overlap or destructive? So every time is the same sign is constructive, like this: constructive, constructive, constructive. This is destructive, destructive, and destructive. So that's why you get the highest energy as a result of this overlap, and lowest energy as a result of all constructive. Okay, and the energy difference here can be measured using UV spectroscopy, the amount of energy that is released when relaxation happens. So when the excited electron goes back to a stable situation, the amount of the energy that is going to be released it can be calculated. The type of questions that you would expect from this like diagram, I'm not going to, for homework, yes. For homework, you would have a table and you can do some calculation. But for exam or for quiz, if I have to give a question like this, I have to provide a table, I have to provide a calculator, I have to provide papers and pencils and all that. So instead, I look for understanding and more of the theory and the application. So what makes the lambda max to increase from a butadiene versus hexatriene? Which one takes less energy is the one with the longer wavelength. The longer the wavelength, the lower the energy is. So that means the energy difference between an occupied and unoccupied for a triene is going to be smaller energy difference compared to a diene. And the difference between a conjugated and isolated. So you will get questions like that. If molecule has no pi bond with same number of carbons, let's say you have a 6 carbon, 3 molecules that each has 6 carbon. One has no pi bond, one has 2 pi bond, the other one has 2 pi bond, but is conjugated. One has 2 pi bond that is isolated. You should be able to compare the lambda max, which one has lower energy, which one has higher energy. Just make sure you know that the greater the value for lambda, the lower the energy is going to be. And that amount of energy can be calculated using a detector from the UV spectroscopy. So the lambda max using the UV spectroscopy can represent or can relate to the number of pi bond and number of carbons that you have in the molecule. If you had only one pi bond, this could be like a 250. But if you have, I'm sorry, if it could have been like 200, or 30 unit less, whatever that number is. But if you have like a 3 pi bond, it's going to be 30 unit more. Because the more pi bond, higher the lambda max is going to be. Example like this, okay? In a system that is a conjugated, you start with like 217. And every time you add another carbon, you're adding like a 10 unit to it. But going from like a 2 pi bond to 3 pi bond, you're adding 30 units. But you're adding a carbon, you're adding only 10 units or 5 units. Sometimes just for CH3 is 5 units. The greater the number of pi bonds, the higher the lambda max is going to be. So for each pi bond, you add 30, and for each alkyl group, you would add 5 groups. 5 value, or 5 to the lambda max value. The lambda max for which one would be the greatest? Number of carbon is the same for all. And without looking at the answer, can you tell me which one would be greatest? I guess I'm going to have to number it. 1, 2, 3, and 4. Lambda max for which one would be the greatest? Four would be greatest because you have 3 pi bonds and all of them are conjugated. 3, you have 2 pi bond, but it's conjugated. And then for 2 is trans. Okay. Is trans. And for 1 is isolated. So it's going to be the highest energy or shortest lambda max.